All right, we have reached the final section of Unit 6, and this section is all application problems, and these application problems are called exponential growth and exponential decay, very much like the first section of this unit when we looked at the graphs of exponential growth and exponential decay. We're now just going to apply them to an application setting. So, quick reviewing, if we have exponential growth, for our application purposes today, if we're dealing with exponential growth, we're going to write them in this form. So notice this formula looks very similar to the PERT formula that we talked about at the beginning of this unit. This little a sub 0 is one term, and what that stands for, that is going to represent our original amount. So, how much we started with. And then remember, E is a number. It's that 2.72 roughly. K is going to stand for our constant value. And T is going to stand for our time, whatever time frame we're dealing with. Now, if it's exponential growth, that means our constant K is greater than 0. That is what is going to make it exponential growth. So then the exponential decay model uses the same exact model, except K is going to be less than 0. So this first example says, in 1970, the U.S. population was 203.3 million. By 2010, it had grown to 308.7 million. Find an exponential growth function that models this data. So here's my model. And I want to start filling in information that I do know. What was my original amount, or my starting amount? In this case, my starting amount was 203.3 million. And then I have E. Now notice they didn't tell me a constant. They didn't tell me what K was, so I'm going to have to leave that as K. But I do know a time frame. They want me to look at from 1970 all the way to 2010. So if I were to subtract those years, my time frame is 40 years. So notice there's one value that I haven't used yet. It said by 2010, I had 308.7 million people. So your ending amount, your final amount, is what A is. So that's what we're going to set it equal to. So usually what you will see on these application problems, you'll have enough information where we need to actually first find K. We need to find our constant. It's very much like we did in a previous unit on the variation problems, where we had direct variation or inverse variation, and we had to first find K before we could answer their question. It's very similar here. So I want to solve this equation for K. So the question is, how do I go about getting K alone? Well, the first thing I would want to do is divide. Now, to try and keep our answers as exact as possible, I'm not going to put this into a calculator yet. So I'm going to leave it. It's not pretty, but I'm going to leave it as just this fraction. And on the other side, I'm going to write that as 40K. Okay, so we're a little bit closer to getting K alone. What would I do next? Well, it looks like the next thing that would have to happen, I need to get rid of the E. So what cancels E? Well, we know we can take the log of both sides. I'm going to take the natural log of both sides. Again, I'm not going to do a calculator yet. I want to wait till the very end to try and put all of this information in. Now on the right side, we know that natural log and e cancel. So I would just have 40k left. And the last step to get k alone would be to divide by 40. So this is going to be a test of how well do you know your calculator, or how well can you work with it. So what you're going to do, you're going to take the natural log of 308.7 divided by 203.3. Make sure you close the parenthesis. And then you'll divide that by 40. And I will tell you, if you do this correctly, our k value comes out to 0.01 with rounding. Now, on my math lab, when you work on this assignment, they might ask you to round k to a certain number of decimal places, so make sure you pay attention to how they want you to round. So what did this problem ask me to do? I found k, but it says write the growth function. So if they ask you to do that, they want to know, okay, what does the equation now look like now that I know k? So my final answer is going to be a equals 203.3, my starting amount, e raised to the 0.01 t. So this is the general function, because now that I know k, I can plug in any time frame I want and get a population out. Again, I can plug any time frame in for t that I want, and I can figure out, okay, what would my population look like? This type of application is huge in real life, especially when people are trying to make predictions. Okay, how big can we expect the population to get? Or if you're dealing with sickness, how many people can we expect to be infected? Or how many resources will I have left after a certain amount of time? The power of this prediction is a big deal. Okay, so now look at part B. By which year will the population reach 335 million? So we have our equation already that we wrote. Let me write it down again here. So by which year will the US population reach 335 million? So what would I do with this 335 million? Well, if that's the population I want to end up with, or that I want to reach, that should go in for A. That's like my final spot. And I want to solve for t. I want to know, how long will this take? How much time do I have? So we're going to solve this very similarly like we did in part A. The first thing I would want to do is divide by my 203.3. Again, I'm not going to use a calculator quite yet. Okay, the next thing that would have to go would be e. And to cancel out e, we'll use a log, because that's the inverse, so I'll do natural log. So again, not using the calculator yet. So I know natural log and e cancel, so I'm left with just 0.01 t. And the last step to get t alone would be to divide my 0.01. So now this is where we turn to the calculator and we see if it can get us this answer. So if you do that math in the calculator all at once, you should get out roughly, with rounding, 50. So now we want to make sure we've answered their question. They say, by which year will the US population reach this many people? Well, my answer is not 50. I want to know, what year is it? So this represents 50 years for this to happen, And what was my starting year according to the original problem? Well, our function was modeled off of the starting year of 1970. So if I go 50 years from 1970, my answer should be the year 2020. I went 50 years from my starting year of 1970. Okay, now let's look at some exponential decay problems. And exponential decay is where you're losing stuff over a period of time. You're getting less and less and less of it. Oftentimes, real-life applications of this type of math deal with something called half-life. And those of you that have taken some science classes might be familiar with the phrase half-life. The half-life is kind of what its name says it is. The half-life of a substance is the time required for half of a given sample to disintegrate or break down. So for example, if my half-life was 50 years, if I had an object that had a half-life of 50 years, that means after 50 years have passed, I would have half of that substance left. After another 50 years, I would have half of that left, and so on. I could keep repeating it. So let's look at this example. After 5,715 years, a given amount of carbon-14 will have decayed to half the original amount. Kind of have a typo here. Let's just end it there and find the exponential decay model for carbon-14. So my end goal on this problem is to write the equation, just like what we did on part A on the previous side. So I'm going to write down my formula here. We're going to try and substitute in what we do know. So let's start kind of how we did the other one. How much of the substance did I start with? What was my original amount? Well, that's weird. They didn't tell me. I don't know how much I started with. They just said the original amount. Well, that's great. How do I do this problem if I don't know how much I started with? Well, for now, we're just going to have to leave it as a sub 0. We don't know what it is. And then I have E. I don't know my constant. Well, this is looking great so far. I do have a time frame, though. They said 5,715 years have passed. And now here's the catch with this one. Did they tell me an ending amount? No, but yes at the same time. If they say it took 5,715 years to decay to half of its original amount, I'm going to cheat a little bit and I'm going to say, okay, after 5,715 years have passed, I know I will be equal to 0.5 of a sub 0. So why can I do that? What does that mean? That I'm literally saying there, half of the original amount. Half of the original amount. I know I'm going to be equal to that. I don't know what the original amount was, but I know after 5,715 years, I will have 0.5 of it, or half of it left. So you might say, well, I don't know how we're supposed to solve this. There are way too many variables. Well, something beautiful is going to happen. If I start trying to let's solve for k. We're going to find that constant again. So if I divide by the original amount, just like I did on the other problem, it cancels out, which is great. So it doesn't matter that I didn't know how much I started with. It's gone. So now I have 0.5 equals, I'm going to write it as 5,715k. So the next step to get k alone, I have to get rid of e. So I would do the natural log of both sides. I'm not going to use a calculator quite yet, so they cancel on the right side. And the last step to get k alone would be to divide. Now you can turn to the calculator. So we're going to do natural log of 0.5, and then we're going to divide it by 5,715. And for this one, I'm going to keep a few decimal places out. Again, on MyMathLab, you're just going to have to read the directions. It will tell you how many decimal places it wants you to keep k to. And now my final goal, I want to write the model. I want to write the equation now that I know k. So my equation would be a equals a sub 0. I still don't know that original amount, but that's okay. E and then my k value, t. So that is like my general model or my general equation that I could then use to find out other information. Okay, and the last example here. In 1947, earthenware jars containing what are known as the Dead Sea Scrolls were found by a herdsman. Analysis indicated that the scroll wrappings contained 76% of their original carbon-14. Estimate the age of the Dead Sea Scrolls. This is another huge application of exponential decay. Being able to get a rough estimation of the age of something. This is a big deal, because if we know how old something is, we know the time frame that it existed in, which oftentimes tells us more about a certain population. So, I'm going to write my equation here. All right, let's see what we're working with. Do I know how much of this I started with? Do I know the original amount? I don't. Okay, so I'm going to have to leave that as a sub 0. And I have e. I don't know k. Or do I? Tricky, tricky. Notice here, this is kind of a continuation of the previous problem. Because I'm dealing with carbon-14, and that was the element I was dealing with in the previous problem, I do know k. It's the negative 0.000121. It's the same element. Do I know a time frame? No, and that's what I'm trying to find. I'm trying to figure out how old are these things, so I am looking for t. And now the question is, what am I going to set this equal to? Well, it didn't tell me my final amount, but it did say when they found it, we had 76% of the original carbon-14 left. So notice what I did on the previous problem. I knew I had half of it left, so it's like I set it equal to 50% of the original, or 0.5 times the original. We're going to do the same thing here, except it's 76%. So as a decimal, that's 0.76 of the original amount. So it's the same concept, only I have 76% of it left. So it's okay that I don't know a sub 0, because when I solve, it's gone. So the next step to solve would be to get rid of e, so I know a log will do that. So it cancels out on the right side. And then the last step would be to divide. Make sure you divide by a negative. So this is where we would turn to the calculator. And if I do that dividing roughly to the whole number here, you should see this number out. So what does that mean? Well, it tells me we're roughly 2,268 years old. So that would give me an idea of maybe where they came from and when they existed.